Before we start today, we have a quick announcement from the Hages.
Hi, I'm Yannis. I'm part of the organizing team of this year's summer school of the graduate school, the HGSFP. And I wanted to take the chance to quickly announce or advertise the summer school. It is going to take place in the French mountains at the end of August, August 24 to 28. We have a great program. We have great lectures. There is a lot of free time activity. Yes, exactly. It's a great chance to get in touch with your peer PhD students. And almost all costs are covered by the HGSFP. So if you're interested, you can scan the QR code and register, and then hopefully see you at the summer school in France. And thanks.
All right, so I will hand over to Maria to introduce our speaker for today. Here you go, Maria.
Okay. So we are very welcome. We welcome Luca here. And this is not the first time that Luca is here in Heidelberg, I've learned. It's your second visit after many years. So Luca studied in Italy and is originally from Italy, from a small town close to Milano.
Yep.
Yeah. And then the PhD studies at the University of Vienna, that on the topic of chemical abundances of intermediate mass stars. That was followed by the first postdoc in the UK, in an interesting place called Milton Keynes. I struggle to pronounce. Apparently, in the very middle of the UK, and the place that has no traffic lights whatsoever. Okay, and a very interesting career trajectory. So starting with the chemical abundances, magnetic fields of intermediate mass stars, continued with the first projects, and probably that was really at the very first beginning of exoplanet transmission spectroscopy, which you extended in the near UV regime for the very first time. Very interesting, which was then followed by a postdoc at the University of Bonn, I guess with Fabian, or somewhere close to Fabian, Fabian's era with Norbert Langer. And again, you continued working on the evolution, on stars, this time on evolution, structure, and magnetic fields of massive stars, OB-type stars. And since 2015, Luca is in 2015, you joined the Space Institute for Weltraumforschung, Space Research Institute in Graz as a research group leader initially. And then just, few years ago, 2023, Luca has become the deputy director of the IWF. And now the primary focus is probably on exoplanet atmospheres, which will also be the subject of this work. And in particular, Luca is also a PI of the Walzer F-type mission candidate. We will hear more about Walzer project here in this talk. And Luca is also the instrument scientist of the Pollux instrument on the HWO Habitable Worlds Observatory. That is also a very widely discussed project presently. So I would like to thank Luca for joining us today, and welcome, and please go ahead.
Thank you. Oh, yes. I have. It's okay. I have. I hope you can hear me. Yes. Good. Oh. Thank you very much. Thank you, Maria, for inviting me. Thank you all for being here. So I want to talk about a topic that is actually very common. Every time that we work on upper atmospheres of exoplanets, we handle non-NLTE processes. And in particular, we handle mainly one non-NLTE process, which is photoionization. But here we went beyond that, and we extended it to species that are other than just pure hydrogen. And I want to show you a little bit the history that that we went through for these works. But let's begin with a little physics. It doesn't change the slide. Why? It's stuck there. Why doesn't... We try again. Yeah. Now, okay, good. So a little reminder for people about LTE and non-LTE. So let's start with LTE, which is what we are all most familiar with. It essentially describes the state of matter when the matter is collisionally dominated. And you can then describe the different states of the atoms or molecules using basic simple equations like the Boltzmann equation that tells you the level population and excitation. You can use the psi equation for the ionization, and then velocity is controlled by Maxwellian distribution. We are all very well aware of this. And then we have non-LTE, in which all these equations cannot be used anymore. And this is actually the state of matter. And here the radiation field cannot be any more described by the Planck function. Essentially, the first one is an approximation, while the second one is the reality, is the hard reality for physicists. So let's now move into a world in which the approximation does not exist and only reality exists. Where does reality is then important, and where the approximation doesn't work anymore? Well, typically these are places in which density is very low, like the interstellar medium, or the temperature is very high, like on massive stars. And planetary upper atmospheres are a bit of both. They are typically quite hot. Even the Earth atmosphere is pretty hot, is well above 1000 Kelvin. And they are certainly a low density because you're moving close to outer space. So let's now move closer to planets and see how they look inside. So this plot shows you the temperature of the atmosphere on the x-axis, and you have the pressure on the y-axis, or altitude. So the bottom of the atmosphere is at the bottom, and the top of the atmosphere is at the top. The black line is the typical temperature-pressure profile of a planet, of a closing planet. Okay, this is actually a horrible Frankenstein between the Earth up to here and the hot Jupiter, or up there. Okay, but it just to give you an idea. You have a first temperature inversion down there that on the Earth is caused by ozone. On hot Jupiters, it can be due to absorption from titanium oxide and vanadium oxide. And then you can have clouds here at the bottom, and then you have a giant temperature rise that moves you closer to the thermobase, and the thermobase is defined as the place where the temperature reaches its maximum. And then the temperature decreases. The temperature increase there is due to photoionization. It's the result of photoionization, which is an NLTE process. And therefore, that area is where non-LTE effects become important. Okay? That area is also the place where atmospheric escape is driven. Okay? Where atmospheres get lost to space, And we know that atmospheric loss is the main process that drives the evolution of or the long-term evolution of a planetary atmosphere. This is my personal opinion. NLTE is both horrible and fascinating. It comprises of a large number of physical processes, all different and all controlled by different parameters. We know pretty well some of these parameters, and we know badly some of our parameters. And we're not even sure we know all physical processes. We are aware of everything that's happening, okay? So it's horrible because you have really a lot that you have to figure out before you can even start doing any calculation. But at the same time, I find it extremely fascinating because you are describing nature as it actually is. So this is the exoplanet population, roughly as we know it today. On the x-axis, you have the incident stellar radiation in units of what the Earth receives, while on the y-axis, you have the planetary radius in units of Earth radii. So you see that Earth lies at 1, 1, okay? You see lots of structures here. There are different populations. You have the hot Jupiters up there. You have super Earths, mini Neptunes, you have Neptunes. The structure that you see here is caused by many things. There are biases, observational biases involved, because this is these are the transiting planets. This is a transiting population. Okay, so there are obvious biases here towards longer period planets, for example, and also towards very small planets. But there are also features in the population that are due to a mixture of planet formation and atmospheric evolution. One of them is, for example, the sub-Neptune desert, which is this void of planets here. It's the, oh, great, thank you. So this void of planets here is called the Neptune desert. And that's due to mainly to the escape of planetary atmospheres as planets are born in this area. They are too close and too low mass to be able to retain an atmosphere, and the atmosphere slowly evaporates and the radius decreases and planets then end up here. There is also some involvement here in orbital evolution that we believe plays a role into shaping that. And the planets that we have been mostly interested in, and I'm going to explain why this specific kind of planet, are ultra-hot Jupiters that are the hottest of the hottest planets. Okay, these have very high temperatures above 2000 Kelvin. They typically orbit bright and hottish stars with hottish, I mean, 7,000, 8,000, 9,000, 10,000 Kelvin stars, so intermediate mass stars. And because they are so hot and they are big, they are great targets for transmission spectroscopy, and we have excellent data for these planets. And in this sample of ultra-hot Jupiters, we have been looking at 3 specific planets. I'm going to explain why that's the case. So these are the planets that we have been looking at. We have Kelt 9b, which is the hottest planet known to date. It has an equilibrium temperature of about 4,000 Kelvin. It's the prototype of all ultra-hot Jupiters. And then there are our 2 planets. And you see that all of them orbit stars that are quite hot, okay, well above 8,500 Kelvin. Why we picked precisely these 3 planets? We have to look at the stars, at the hot stars. So this is the emission of the sun as we can measure it from Earth. This is the spectrum. You have the UV here. There is Lyman alpha that's very prominent. And then we have here the extreme ultraviolet, which is dominated by some continuum plus the helium-2 resonance line. This extreme ultraviolet is what drives atmospheric escape on any planet that has an hydrogen-dominated atmosphere. what happens is that the let's imagine to have an hydrogen-dominated atmosphere. An extreme ultraviolet photon comes, it hits an hydrogen atom. What happens is that this energy that the photon carries is high enough to ionize the hydrogen. Therefore, the hydrogen gets ionized, the electron gets kicked out. This electron, if the photon has an energy that's higher than 13.6 electron volt, the remaining energy, okay, so what is left after that 13.6 electron volt has been absorbed, what is left is the electron still holds of that energy. And a fraction of that energy, which is between 15 and 40% of that energy, gets turned into heat. And this is precisely what drives the heating that I was showing you before in the planetary atmosphere that leads to the thermosphere. The cooling that comes above that is because the atmosphere becomes so hot that it starts expanding hydrodynamically. And through adiabatic cooling, essentially it expands. The expansion leads to the decrease in temperature, and that's the temperature decrease that you see afterward, above that. So this extreme UV, it's typical, it's a signature of every sun-like star. Okay? Now, stars like these ones, how do they look like in the extreme ultraviolet? Do they also have this kind of emission? Because if they have this kind of emission, their hydrogen is the thing that heats. The hydrogen photoionization is the one that heats the atmosphere. And this hydrogen photoionization is the main component of the heating, but there may be other heating components that we can't see simply because the hydrogen photoionization is so strong, so dominant. And what we wanted to look at is exactly, are there other heating sources in the atmosphere beside hydrogen photoionization? And here stars come to help. So this is a very busy plot that I'll try to simplify. So you have on the x-axis, you have color of stars. So hot stars are here, cool stars are here. Okay? And then on the different y-axis, you have different indicators of activity of stars. So essentially, whether stars do have that extreme ultraviolet emission or not. Okay? And you see that, so you have X-ray emission, Lyman alpha, various far UV lines. Here's another far UV line, and here the helium triplet in the near infrared. And you see that all stars that have a color that is higher than 0.1, which corresponds to a temperature of about 8,400 Kelvin, roughly, they all have emission. And they have quite a strong emission. Okay? While stars that are hotter than that, the emission is not there. It just dies suddenly. Okay? And these are all indicators, and it's very hard to get proof of this by looking directly at extreme ultraviolet for two reasons. First one is that we only had one mission so far that observed in the extreme ultraviolet, and that was EUV, and had an effective area of 2 centimeters squared. So practically the only intermediate mass star for which we have an EUV spectrum is Procyon. It's the only star for which we have an EUV spectrum. And the other reason, and the reason is essentially that there is the interstellar medium in between that absorbs the extreme ultraviolet radiation, and therefore it's hard to observe in general stars in this band. But the idea that you get is that stars that are cooler than about 8,400 Kelvin, they have extreme UV emission, and therefore they show that big heating in the atmosphere. Okay. They most likely, these planets most likely have an hydrodynamically escaping atmosphere, and which is driven by hydrogen photoionization. Stars that are hotter than that, they don't have this kind of hydrogen photoionization. They don't have this kind of heating in the upper atmosphere. So how are they going to look like? What's happened there? That's the question. let's look again at stars and how we picture them. So we have the sun, which is the orange line. This is a spectral energy distribution. The sun, which is the orange line. And then you have stars that are somewhat in between the sun and this magic number of 8,400 Kelvin, which also have extreme UV emission. And here you're just taking the sun and increased it in such a way to match what Procyon shows. And then you have hotter stars that instead just the EUV dies down because it's essentially the black body emission, okay? That in the EUV just goes down. All right, so let's start to look at these planets, the planets that orbit these kind of very hot stars, how the atmospheres look like. So the first one we looked at was Kelt 9b. You see here its transit is very beautiful, it's quite deep. We can measure the mass through radial velocity quite nicely. It's a very hot planet, as I told you, it's about almost 4,000 Kelvin, its equilibrium temperature. What we did, because we're interested in non-LTE processes in the upper atmosphere, we had to use a non-LTE code, and we decided to essentially do violence on Cloudy and convince it to work for planets and not only for anything else that's not planet. This is a quite famous code. It has been mostly used at the beginning to do AGNs. It comes originally from Osterburg, but then Fairland has increased a lot. It considers a bunch of elements, all elements up to zinc, and many molecules. We managed to incorporate it into planet atmosphere code and managed to then get the temperature pressure profile. So let's see how this looks like. That's how the temperature pressure profile that we got for Kelt 9b looks like. It's this black line here, okay? And this is the temperature pressure profile that we got with Cloudy in comparison with what typically is obtained with LTE codes. Okay, and you see there is quite some difference there. So then the question obviously is this difference due to non-LTE effects? So luckily, Cloudy, you can almost completely switch off non-LTE and run it almost fully in LTE. You can't fully kill the non-LTE, but it still works. So we run it in LTE and we get a temperature pressure profile that resembles very much that of the other code. Then the question comes, well, now that we know that extra heating is due to non-LTE effects, what actually causes that extra heating? So the first thing that we did was, good, let's try to figure out which are the elements that drive that extra heating. Okay, so we removed from the atmosphere one by one all elements. And none of the elements except two did anything to the temperature pressure profile. Only two changed it. And these are iron and magnesium. So this is again the black line is again the temperature pressure profile you've seen before. You remove iron and you get a very cold temperature. Okay, the temperature goes down. You remove magnesium, temperature goes up. So iron is a heater and magnesium is a cooler. How comes? So what happens is a combination of things. So these stars have the peak of their emission in the near ultraviolet. Okay? In the near ultraviolet, it is also where iron 2, so singly ionized iron, has its largest and densest band of lines. It's up here. Okay? Here, in this region. So the planet forms because it becomes hot if it thermally ionizes iron. The abundance of iron 2 increases. By increasing the abundance of iron 2, essentially iron 2 gets overpopulated. By getting overpopulated, what happens is that that radiation, which is the peak of the emission, is absorbed even stronger, even more by the iron 2, because the iron 2 lines lie exactly there where the peak of where the peak of the stellar emission is, and the process continues and it keeps heating and heating and heating. Okay, and that's why iron causes so much heating. Magnesium instead is a natural coolant, does radiative cooling mainly through the magnesium 2H and K lines, and the result is that magnesium gets both magnesium 1 and magnesium 2, they get underpopulated. And the underpopulation then prevents the cooling, and that's why the heating increases even more. Okay? So what is important here also to understand is that the temperature pressure profile of these planets is also controlled by the abundances in the atmosphere of these planets. Because if you get more or less iron or more or less magnesium, the temperature is going to change. If the temperature changes, the mass loss of these planets also changes, and the evolution of these planets also changes. And it may change quite significantly. Here you have how the temperature pressure profile in the upper atmosphere changes as a function of the abundances of the two elements. And you see that even by simply increasing, for example, twice the metallicity, so increase twice, you make 2 times supersolar metallicity of both iron and magnesium, you still get a different profile. So the two effects don't cancel each other out, precisely. Okay? So now a logical question that you should probably pose me is this just the product of my fantasy or Claudi's imagination, or is this real? As I told you at the beginning, these planets are beautiful also because we can get beautiful data. So let's see whether the models actually match the observations or not. One of the very first observations, transmission spectroscopy observation of KELT 9b has actually been done here, and that's the Jan and Henning 2018 Nature paper. It's this green line here. It's the H-alpha detection of KELT 9b. And at the time, they had an LTE model because there was nothing else available, and they practically got this red line. Okay, and you see this giant difference. And the obvious thing at the time was, look, it's a super hot planet. It's very close to the star. It obviously has an escaping atmosphere. Escaping atmosphere also means expanding. Okay, driving, expanding. It means that the atmosphere is extended, and that's what they believed, that this difference was due to the expansion of the atmosphere that they could not account for because that model is hydrostatic. Now, let's see whether instead just simply having a hotter atmosphere without the need of hydrodynamics fits the data. And incredibly it does. And it does remarkably well, as you can see here. Okay, so this is the non-LTE profile of H beta, and this is the non-LTE profile of H alpha, and it fits the data very nicely. And why is the case? It's simply that if you have a hotter atmosphere, the pressure scale height increases, the size of the planet increases, the size of the atmosphere increases, and therefore the size of the signature in the transmission spectrum gets deeper. Okay, it's just that, nothing else. It's just the outcome of a hotter atmosphere. Good, then that was just luck, just hydrogen. Obviously, just the main thing that's in there, but maybe you can't fit the rest. So let's try with iron. It does fit. The green line is the model, and you see the data in non-LTE. It fits the data remarkably well. What I want to stress here, it's very important, is that there is no fine-tuning, there is no fitting of anything. We just throw the system parameters into the code. It makes one forward model. It takes a week, but it does one forward model, and you get that spectrum that fits the data. Good. Then we try to go a step beyond. Can we actually predict observations? So this is the transmission spectrum that we modeled, that we obtained for KELT9, and you see various features. And there is one nice feature. You see here the deviation from LTE. There is one nice feature here, right? That has a very strong deviation from LTE. That thing is the oxygen 1 triplet that many of you are probably familiar with. So the same data that have been used to detect H alpha, the green line in the previous plot, they cover also this triplet. These are Kermenes data that some of you are very well familiar with. They were sitting on the archive, and you see that the strength of this line is not too different from this one, which had been detected in this one. So we thought, well, if H alpha could be detected in those data, the oxygen triplet should also be detectable in those data. And indeed it was detectable in those data. This is the oxygen triplet, and the pink line here, purple line here, is the NLTE model that again fits the data. Okay? So probably it was not by chance that the model actually predicted a much hotter temperature. Let's move to the next planet, which is KELT20, and we went through exactly the same exercise, expecting not to be able to fit the data. You know, you get lucky once, probably you don't get lucky twice, but we got lucky twice. So this is then the Balmer lines. You see the observations, and you see the transmission spectrum. Now the transmission spectrum, the model cannot fit exactly the data for a very simple reason. The model assumes that the entire atmosphere, also the terminator, which is the area that we probe, looks like the substellar point, which is the hottest part of the atmosphere, which is not the case. Okay? But it takes 1 week to compute one model. You can imagine what that would take in 3D. It would take forever, right? So we can only stick with this. So again, was this luck that the hydrogen is fitting? Well, no, because also iron 2 is fitting again. Let's move then to the third planet, which I think is probably the most interesting of the three, and it is WOSP 178. And it's the most interesting because we're moving away from the optical. We're going into the realm of the near ultraviolet, where most signature of upper atmosphere and escape is present. And this comes from a Nature paper from Josh Lotringer. And you see this rise in the near ultraviolet. They could not explain it without adding absorption from silicon oxide. And that was, at the time, proof of the detection of silicon oxide. And we thought, okay, let's try. We have data here that finally tend to move towards the upper atmosphere. Let's see whether we can fit this data as well or not. So we did again the same exercise. That's the temperature pressure profile that we got. So it's again much hotter than what is expected in LTE. And we have then computed the transmission spectrum, and again, it fits the data remarkably well. You see, this is the model in black, the non-LTE model, and it fits the data very well, without the need of any silicon oxide absorption. There are actually no molecules in this model except for H2, okay, and H3+. So, which is the result? Why is that the case? Again, hotter atmosphere means a more extended atmosphere of the planet, and therefore the signature in the transmission spectrum goes up, and that's what you see here. Okay? You can see this also, so I'm now taking off my exoplanet goggles and I'm putting on my stellar goggles. Okay? What I'm looking here is the outcome of the fact that the stars do not have extreme ultraviolet emission. Okay, or at least they have it extremely low extreme ultraviolet emission. They don't look like the sun. What's the difference between then the sun, or a star like the sun that has extreme ultraviolet emission, and stars that are much hotter that don't have? What is the difference? The difference is the convection, right? So we can actually use these planets to probe convection in stars, to probe the limit, the temperature limit of convection in stars, up to which temperatures do stars have surface convection. And that's what one can in theory do. So you see here, this is the HR diagram, and color-coded you have turbulent pressure versus total pressure. Essentially is where you see colors that are not this purple, you have strong convection. Okay? And these are this is the result of MESA models. And you see that there is a cutoff there. But now, thanks to this planet, we have the possibility of identifying where exactly in temperature across on the HR diagram that cutoff is, without having to look directly at the extreme ultraviolet emission of the stars, which we practically cannot do, or at least we cannot do yet. So we can answer questions like, in which region of the HR diagram do we have chromospheric and coronal emission? Do these stars have wind? Do we know whether intermediate mass stars have winds? We have absolutely no clue whatsoever. We can test stellar convection models, and hopefully these can also help further understanding for where chromospheric heating comes from. So I have a few takeaway messages that I'm also using to do some brutal advertisement. So non-LTE effects in metal lines play a very important role because they drive the temperature pressure profile, that they essentially drive the temperature in the upper atmosphere, which then drives the evolution, the atmospheric evolution of this planet. The question is, what about cooler planets? And I don't know, we haven't tested it yet. Therefore, the abundances of some of the metals, and specifically of iron and magnesium, they are very important. And they are not that trivial to measure properly. And the other thing, and this is coming then important for my next slide, is that ultra-hot Jupiters, they have extreme atmospheric escape, because from the temperature pressure profile that we got, we can then infer the mass loss rate, which is indeed very high. So they do have an escaping atmosphere, it's just not hydrodynamically escaping. But to probe that, we require UV observations and at a resolution that is larger than 1,000. Because the data that you have seen before from Josh Lotringer that were coming from HST, and they were done at a resolution of 20. That's by far not enough. So to solve this conundrum, we devised WALSER, which stands for Wideband Atmospheric Laboratory for Transiting Exoplanet Research. So this is an ESA F3 mission concept, and I have the pleasure or displeasure of being the lead proposer. Is equally PI'd by Austria and Switzerland. We have a large consortium. The core science is on exoplanets. The idea is to cover simultaneously the near ultraviolet in this band and the visible band in this wavelength range, spectroscopically at 3000 resolution, and at the same time the near infrared with a photometer. All of this is done simultaneously in one shot. You see here we have a 35 centimeter telescope. We have a full mirror first, and then we have two dichroics, and the dichroics help us splitting the light in the different channels So the near UV, the visible spectroscopic channels, and then the near infrared channel. The photometry that is used then as pointing in the loop with the platform to control the pointing, to stabilize the pointing of the satellite. Primary science, as I said, is on exoplanets, and the idea here is to simultaneously characterize the lower atmosphere, mainly from the near infrared and the visible, and the upper atmosphere from the near UV of planets, of giant planets mainly, and to identify any connection between the two parts of the atmosphere. However, there are also secondary surveys, and we would be happy of getting more of those. We have surveys on stars, mainly on high energy emission, and we also have surveys on the solar system. We're going to look at the evaporation of comets and plumes of Enceladus. And if is accepted, there is 25% open time. The proposal has been submitted, has gone forward into the step 2, so the step 2 proposal has been submitted, and in November we will know whether we will be one of the 2 missions that will do phase 0. And then in November next year, ESA will finally select the mission that will fly. Just to give you an idea of the kind of data that we're going to obtain, this is the transmission spectrum of WASP 178. You may remember the plot, this plot I've shown you before. So you see the data here. So we took the black model and put it into the Walzer simulator, and the green spectrum, the green transmission spectrum is what we got. And this is compared after 10 transits, and this is compared after 1 transit of HST at very low resolution, which are the red data points. And you see that at 3000 resolution, indeed, we start looking at seeing spectral lines here. The other instrument I like to advertise is called Pollux. It's a European instrument candidate for the Habitable Worlds Observatory. I have the pleasure and displeasure of being the instrument scientist. The instrument is led by France. There are 2 co-PIs. It does everything. If this works, is unbelievable. So it covers from, we're still debating between 97 and 100 nanometers up to 1.75 micron. This arm, the far UV arm, these are 5 high resolution spectrographs. The far UV arm works on its own, separated from the rest, while everything else, so the 2 UV arms, the optical and near infrared, so from about 120 to 1.75 micron, all at the same time, simultaneously. The resolution is high. We have 100,000 FR UV, although we are still debating about that, and 65,000 everywhere else. Again, we're still debating a little bit about this. Optional is polarimetry. Every channel has a dedicated polarimeter that can be removed, so you can do single point spectroscopy or single point spectropolarimetry, up to you. Point source. And in the UV, in spectroscopy mode only, we can also have a small slit of about 3 arcsecond length. If you're interested in joining the consortium, you can just scan the QR code, and we'll bring you to a web page where you can put in your email address and get information and notifications from us. We are currently collecting science cases, so if you want to contribute, please talk to me. And you may not be a fan of Pollux, but if you're an astronomer, I think you should be a fan of HWO. It's an 8-meter telescope in space. I don't think it gets better than that. Therefore, you can join us at the European HWO conference that is going to be held in Paris this winter. The other take-home message is about stars. So these kind of planets, they can help us contributing understanding the high energy emission of these stars. And there is a new mission that hopefully is going to do that in a few years, and that's called ESCAPE. It's a small explorer NASA mission. Here instead I have the pleasure of being the science team. It's essentially it wants to survey the extreme ultraviolet emission of stars, mainly for purposes of studying habitability of planets orbiting around these stars. But part of the science is also about hotter stars. And the idea is to use technology that has come up since the EUVE time, we're talking about the 90s, to enable observations of nearby stars. Remember, EUV, I told you, had an effective area of 2 centimeters square, so about this size. And with ESCAPE, we do about 100 times that. So we have a much larger effective area. And we should be able definitely to observe the extreme ultraviolet emission of stars. And we hope also to detect CMEs directly. And with this, that's all I have. Thank you.
Thank you for this very interesting talk. I will open the floor to questions, particularly from students and postdocs to start.
Thank you for the interesting talk. Maybe I didn't really fully understand. So you're saying that the composition of the atmosphere matters, right? But for the plots you were showing, what composition did you put into the planets when you made those models? Because the uncertainty on the metallicity, for example, for the star was like 0.3 dex, which is ×2. And ×2 you showed also goes either direction depending on iron and magnesium.
So in these models, it's a solar composition. The composition changes a little bit the hydrogen line profiles, but not too much. Obviously, it changes the line profiles of the metals, for which you change the abundance. And indeed, we are in the process of fitting the abundances of the atmosphere of Cat 9b. And we find the abundances not to be solar. But I cannot say more.
Hello, thank you so much for the very interesting talk. I have a question about the NUV flux from the hotter stars. So it seems from the talk that thermal inversion and also the escape is caused on ultra hot Jupiters orbiting hotter stars are caused just by the NUV flux, right? Without the EUV emission from a corona. But what about cooler stars? Like, do they simply not have the NUV flux to heat up the iron lines? Because if they do, it seems to me that thermal inversion and escape must happen in ultra-hot Jupiters or exoplanets orbiting stars with a corona, because like a combination of two heating mechanisms, right? Like especially for planets with high metallicity.
That's exactly right. So you have the hydrogen heating, the photoionization that's heating the atmosphere.
Mm-hmm.
The hydrogen photoionization, which is dominating then. And then on top, you have metal line heating, which is currently not taken into account.
Okay.
So we got to figure out how much that is in comparison to the heating from hydrogen photoionization. The only issue is that in order to do that, you need an hydrodynamic code. We do have that. We managed to implant Cloudy into an hydrodynamic code, but we haven't done the runs yet.
Thank you very much.
My question is, do I understand it correctly that the wording non-LTE is, for you, another way of saying photoionization? Because NLTE can have different meanings, right? You can,
Yes.
I mean, if you are doing line radius transfer, NLTE is the population levels, right? And that's not what you're meaning here, right? Or
What I'm meaning is that all the level population and all these things for how to explain this? So in planets orbiting cooler stars where there is hydrogen photoionization, these are non-LTE models, okay? Because they do photoionization, for example. They do many other things as well. Many other non-LTE processes. They do the full level populations for hydrogen and everything. So it's full non-LTE, but it's just hydrogen, or just hydrogen and helium. What I mean here when I say non-LTE is not only hydrogen or hydrogen and helium, but it's the full non-LTE physics for every element up to think. Okay? When instead I mean LTE, that's really pure LTE for everything. So there is no photoionization whatsoever. I can understand there can be a bit of confusion here, but it comes from the fact that these upper atmosphere models that do only hydrogen or hydrogen and helium, they are not called non-LTE, although they are. That's from where the confusion comes.
Thanks for this very nice overview of what difference LTE or NLTE does make in these hot atmospheres. At the end, you talked about these very cool instruments and telescopes, and I'm wondering about the, let's say, survey capabilities of the Habitable World Observer. And I come from that, from the point of view of the extragalactic community. If I look at James Webb, it does fantastic by giving us maps of nearby galaxies. Can we do something similar with this new planned device? Is this something that is in the science case of the Habitable World Observatory? So Walzer is a survey machine. Okay, but it's a 35 centimeter telescope. HWO is going to have one survey that's going to be run by the coronagraph. That's I believe the survey. It's called Habitable World Observatory, right? It's driven by the name. There's going to be one survey, I believe. The other instruments will have their own timeshare to begin with, and then it will be open time. And since there will be open time, we've seen that with time on HST, the number of surveys has significantly increased, and I believe it's going to happen the same.
Hi. Yeah, so I think there's a place in your talk where I got a bit lost, because you started saying that your atmosphere heats up with photoionization and it cools expanding. And then you show these models where you find a hydrostatic atmosphere that just cools radiatively thanks to these magnesium lines. So, but then you said that you fit these hydrostatic models to your data and you can infer huge mass loss rates. So how can you link this hydrostatic model to a mass loss rate?
It depends where the mass loss rate, let's say where the mass loss happens. The mass loss happens for this planet essentially above the exobase. Imagine it as a super duper genius escape. Okay, in which there is no hydrodynamic transport. That's how you can picture it. It's as I said, that there is no or very little motion of material moving up. It's there, it's hot, therefore it's expanded. It's not expanding hydrodynamically, it's expanded because it's hot. And then the upper layers, the uppermost layers, they reach the rush lobe and then they leave. Right? It's not that there is nothing pushing, there is no energy that pumps material from the bottom, which is what would happen if you would have for planets orbiting cooler stars. it's slightly different. Yeah.
Then I think we had one last question.
I can, if you want, I can show you a plot. I had to remove it because it's very detailed, but I can show you a plot that probably helps you clarifying this point.
The final last question. Okay, so this is maybe a question to Luca or to all exoplanet experts here in the audience. Something has been bothering me for a while. So when we discuss about abundances in exoplanet atmospheres, we are so used to set them to solar values. What do we know about the exoplanet atmosphere composition of Jupiter atmosphere? Is it the same like the sun?
It's very similar. It's enriched in metals. It's not exactly solar. It's a bit enriched, but it's not very
Jupiter
different.
has the atmosphere composition of Jupiter is the
like
same like the
twice-
solar value
Like twice,
in mass number and in density,
like twice solar. It's not much more than that.
but twice is a lot. And
Twice
why
is a lot.
does this difference come about?
But it's even more as you go to smaller planets. So Saturn is even more, and then Neptune is even more. Uranus is even more, and Neptune is even more.
So is there a good reason to assume that the solar composition is a good starting point for all this atmospheric modeling? Is there a good physical reason for that?
No, it should be the stellar.
Well, I mean, stellar in general, not just solar or stellar or whatever. I'm particularly looking at Duncan here. That's not so obvious to me, but okay.
One of the good things of these kind of planets is that they are so hot that they look like stars. So there are very few molecules because they are so hot. So you can actually go and measure the actual elemental abundances without having to know the chemistry. Because if you measure the molecules, you've got to know all the chemistry that's behind that leads you to that molecule. And from that, then infer the elemental abundance. In these planets, you don't need to do that. That's what we're doing.
All right, Maria's getting ahead of herself. All right, there will be drinks and dinner with the speaker. If you're interested to join, Nick is organizing that. Come and talk to him. And with that, let's thank our speaker again.
Thank you very much.